So this is E685 VLSI broadband communication circuits. So before going into the introduction for the class, so I'll just say a few words about the tablet. I chose this mainly because I could also record the lectures and put it on the web, particularly because there is no book for this course. But I don't recommend that you stop taking notes completely, because you also learn something when you write down. You don't learn by passively reading. Even when you're reading a book, it's best if you work through the steps. It's not like reading a storybook or something. So by watching Baywatch, you won't become a lifeguard. Similarly, by just listening to the lecture, you can't absorb everything that's going on. But it will reduce, hopefully, the drudgery of reproducing every diagram that I write, because you all can always refer back to it, or at least you have a record of the whole thing. So, and also remember that this is an experimental stage and technology can fail at any time. So keep a backup. Also, right now what I'm doing is using the tablet more or less like the traditional blackboard. So if you can think of some other ways of using it, which is very different from how it is used now, then of course I would be welcome to all suggestions. So what is this course all about? So it says broadband communication circuits. So basically what we will talk about in this course are circuits that are used for digital communications. And digital communications basically means sending digital data bits from some place to some other place. So I'll just say across the channel, and the channel can be anything. So as you know, digital data is transmitted in mobile phones, in Ethernet, in USB, in a variety of applications. And this the channels that we consider in this course also include cases where you are not particularly interested in telecommunication, meaning if you have a PCB and you want to send data from one side to the other, you may not think of it as a communication link, but it is, right? The idea is not to send messages from one person to another. It's just to have digital data on one end appear at the other side. Now, what about broadband? What do we mean by broadband? So if you look at the spectral density of any transmitted signal, it will occupy some extent, some finite extent. We can't deal with infinitely large bandwidths. So let's say it is something like this. What this implies is that in this range, there is a lot of spectral content. Outside that, it has negligible spectral content. And the region of frequencies over which it has significant energy is known as the bandwidth. And the signal is centered around some center frequency Fc. So we use the ratio Fb by Fc to distinguish between narrowband and broadband signals. So if Fb by Fc is very small, so let's say much smaller than 1, it's a narrowband signal, and if it's of the order of 1 or even more, it's a broadband signal. So the spectral density of a broadband signal might look like this. It may extend all the way up to DC or something close to DC and up to some high frequencies. So in this case, if you think of this as the center frequency, the ratio of bandwidth to center frequency is 2. Where do you see narrowband signals? Have you seen examples of either of these cases? Where have you seen narrowband signal? Where do you see broadband signals? Mobile applications will be narrowband signals. Why would you use narrowband signal? Why would you use broadband signals? Broadcast radios are narrowband. So it is related to that. So when you have a common medium across which you have to transmit multiple channels, you have to support multiple channels, then you will opt for narrowband, because using different frequencies is one way of distinguishing between different channels. So if you have a common medium like air, and all signals have to be transmitted across the same medium, then one of the ways and the most obvious way to distinguish between them is to use different frequencies for different signals. So these things necessarily will be narrowband. So you have a certain usable range of frequencies and you divide it further into channels and you use that for communications. So this is typically the case for transmission over a common medium like air. Now the medium may not always be common, meaning for every signal that you need to transmit, you can have a pair of wires between point A and point B, wherever you want to transmit. In that case, you are not constrained by this. You can occupy the entire range of usable frequencies. I have not defined what usable frequency is. It depends on the situation. Okay, it basically means the range of signals that you can conveniently process. That's all. So if you have transmission over a confined medium, for instance, a pair of wires, right? So if you have two separate pairs of wires and you transmit signals on both of them, they don't interfere with each other, at least not to a significant degree. But then if you transmit two different signals in air, they'll completely interfere with each other, right? One will affect the electromagnetic field just as much as the other one will, right? So in this case, maybe you have a broadband signal. So when do you transmit signal over wires? What are the examples that you know of? Telephones, yes. Ethernet. What else? What other? Say, optical also. In the optical domain, it is narrowband because the optical frequencies are necessarily very high and the bandwidth of the signals that you transmit is small. But yeah, actually we will deal with some of those things also. What else? Where else can you think of digital signals being transmitted over pair of wires? TV channels. Actually TV, now cable TV is transmitted over cable. But there also you have the same medium for various channels. So you have to have some narrowband requirement. So there is a huge variety of examples. One is sending signals over telephone lines. Telephone lines, of course, traditionally carried voice in an analog fashion. But now there is digital data. If you look at DSL, it is digital and there are various flavors of DSL, right? And another common example is Ethernet. You've all seen and are familiar with Ethernet. And you have digital data transmitted at various rates depending on how old your modem is. So you see things like 10, 100 and 1000 base T. It refers to whether the data is being transmitted at 10 megabits per second, 100 megabits per second or 1000 megabits per second. And people are currently working on making Ethernet modules for 10,000 megabits per second or 10 gigabits per second, okay, over almost the same pairs of same kind of cable. So the speeds are increasing constantly. Then what else? We have USB. You have all kinds of devices working off USB, and it's not necessarily something like a mouse which needs only a low speed link. It can be a high speed link also, and now it is up to 480 megabits per second. Then you have optical links. Now if you look in the optical domain, these are narrowband signals, but we will need broadband circuits to process these signals. That we will see afterwards. Okay. When we translate the signals from optical to electrical domain, you will end up with broadband signals, and you will need broadband circuits to process them. Okay. So these are all examples where it is like a communication link, meaning you are explicitly thinking of sending data from one side to the other. And the examples where that's not the case, but you do have some similar behavior, are you have printed circuit boards and you have to transfer data across printed circuit boards. I mean, that may be simply because you have two chips. So this is a printed circuit board. You have chip number 1 and chip number 2. So this could be the processor and this could be the memory, and you have to transmit data between the two. And as you know, the speeds are increasing every day, right? So anytime you have to transmit digital data between these, you will have to deal with the same issues as in these cases, where you think of these being explicitly as communication links. Okay. So this is one example, and there are what are known as backplanes. Backplane is nothing but a large PCB, which holds a large number of small PCBs. They are known as line cards. So finally, all of your let's say Ethernet traffic goes through some switches and so on. So you can see some of these backplanes in those large switches. So you have many links which are put together, and then you have to connect between various links, and you will have backplanes. So it's nothing but a large PCB with PCB traces up to 1 meter. Okay. So the kind of issues that you have to deal with in a PCB trace are similar to what you have to deal with in telephone lines. Maybe the frequencies are different. Maybe the exact magnitude of signals are different, but the kind of things that you will see, the kind of problems that you will see in transmitting data will be the same. Okay. So these are also broadband communication links. Now you can go even further inside the chip itself. So on the chip, I don't know how many of you are familiar with how an IC is made. An IC is nothing but a piece of silicon on which, with lithography, you fabricate the transistors and the interconnects. And the chip is packaged inside some plastic or ceramic enclosure, and the pins are brought out. You have definitely seen chips in your lab and so on. So, typically you have a piece of ceramic or plastic with pins on the sides, or it may be at the bottom. And inside the package is a cavity in which you place the silicon chip, and the chip is connected to the package through what are known as bond wires. So you have small wires about 25 microns thick connecting the chip to the package, and on the chip you have traces just like you have on a PCB connecting the bond wires to the pins. So this is how you make connections between the outside world and what is going on the silicon, right? You have the connections on the package and bond wires, and if you have to transmit digital data across these, again you will encounter, it turns out you will encounter the same problems as you do in any other case, okay? So even that falls under, in some way, under broadband communications, okay? And on top of it, you can have a single chip, and you have two different parts of the chip, and you have to transmit data from one part to the other. And even there, it's the same thing. Everything is scaled down in size, that's all. The wire is much shorter, but it's also much thinner, okay? So it turns out that you will have the same kind of issues. So a link between two parts of the chip also classifies as a broadband communication link. Now, depending on the situation, it may be easy or difficult to transmit data across any of these things. So first thing is, what is the potential issue that you see? We have a pair of wires and you want to transmit data. So what is the big deal? You put some voltage on this side and the same voltage appears on the other side, doesn't it? What is the problem? What are the problems in communicating data across a pair of wires? Because the wire by definition is a good conductor, and you apply a voltage on one side and the same voltage should come to the other side. So why do we even have a course about the whole thing? Okay, parasitic capacitances. So what happens? Where is the parasitic capacitance now? In this situation. So this is the kind of scenario that we are discussing, right? Every scenario that I outlined before, whether it's Ethernet or connections on a chip, is something similar to this. You have two wires and you have to transmit data across it. So what is the problem? So this serves as a good model for everything that we saw before. Now, what is the problem with this? Why do we have to study this, or why do we have to even think about transmitting data, right? You apply voltage on one side and it should appear on the other side. What are the problems that you see? So, okay, where is the capacitance in this? Between the two wires. Okay. So, what is the problem now? So, what happens is that is true. Basically, a wire is not a perfect conductor, and firstly, a pair of wires are in proximity to each other, so there is capacitance between them. And since the wire is not a perfect conductor, it has some series resistance, and because it has some finite extent, it also has series inductance. Okay, so you have the wire really is made up of these resistive, inductive and capacitive elements, okay? And in reality it is distributed. It's not like you can identify some particular part as being a resistor or some other part as being an inductor, okay? And a different part as being a capacitor. The capacitor, resistor and inductor are all present continuously. So that is known as a distributed system, okay? So you can think of the wire as being made up of RLC sections like this and so on. Okay. So this is the reality of the wire. It's not a perfect conductor. It has parasitic resistance, parasitic inductance and parasitic capacitance. The next question is, so what? What happens because of this? What is that? That's okay. What is the problem with that? Okay, firstly there is a lag in voltage, meaning the output doesn't appear instantaneously. Yeah, actually the problem is that it is dependent on frequency. Okay, we'll go into details of that later. In fact, a lot of these things just introduced without describing in detail, but the whole course is about that. This is just the introduction. Okay, so let's take a very simple case where we'll say that the inductance is insignificant. Okay, and also we'll make a further approximation that we don't need this distributed structure. We'll simply consider one resistor and one capacitor. Okay, so let's see what happens in that case. Let's say our perfect wire was replaced by something like this, and as I mentioned earlier, I am interested in transmitting digital data. Okay, so let's consider a case where I am sending across a bunch of bits, and -1 volt stands for my symbol 0 and +1 volt stands for symbol 1. Okay, can you see properly on this, or should I write bigger? So what do you get out? Is there a problem? So the idea of any communication link is that you send something that you don't know on the other side. Obviously that's why you are sending it, and you should receive exactly what you sent. That's an ideal communication link, or that's what you aim for. Okay, now this is my message. I have 10011, something like that. Okay, some arbitrary bit pattern. What do I receive? Depends on the bandwidth. Okay, so assume something and tell me what happens. So it depends on the values of R and C, but we know the step response. So we firstly can recognize that this digital bit stream the digital bit stream here can be broken up into a number of steps, and we know the step response of the RC system. So we can reconstruct the output signal. So depending on, let's say R and C are very small to start with. In that case, what you get is, let's say you send this. This is what you send, and what you receive will be. So it starts from here, and the edges won't be sharp, right? Because the capacitor voltage cannot change abruptly. It can only change gradually. So it will do something of this sort. This is for some particular value of RC, let's say. Now I go on increasing the value of R and C. What will happen? The time constant will become longer and longer. So maybe it will do this. And it can even become worse than this, in that even in the time required to transmit two symbols, it has not gone all the way to the steady state value. Okay, so this figure is a little cramped. So let's re-examine the same thing, and this time what I'll do is I'll just transmit a single 1. This is 0, which is -1 volt, and this is 1, which is +1 volt. So firstly, how do we distinguish zeros and ones at the output? So one thing that we have to recognize here is that what you get at the output is an analog waveform. See, what is a digital waveform? It consists of a discrete number of levels, that is y-axis is quantized, whereas what we get at the output is something like this. In this case, the y-axis is definitely not quantized. So firstly, how do we distinguish between ones and zeros at the output? What is the threshold here? 0 volts. Because we are using symmetrical voltages about 0 for our 0 and 1 symbols, our threshold is 0 volts. So let's say I look here, and if it is above 0 volts, if it's positive, I say it is 1, and if it is negative, I say it's a 0. So I don't care about the exact voltage, I'll just say that if it's greater than this, it's 0, 1, and otherwise it's a 0. Okay. So that gets rid of the problem of having an analog output, meaning having a continuous time output like this with continuous values, right? So even if the output voltage is only 0.9 volts, we still recognize it to be symbol 1. But what happens as we increase the time constant RC? So it can do this, okay? If the time constant is large enough, it can do this where it has barely, the input goes from 0 to 1 and back to 0. The output starts from a negative value because it has reached steady state with -1 volt, and then it barely reaches the positive values and comes down. And it can be even worse in that it may not even reach 0 volts. Okay, you can always make R and C large enough that this happens. So here it doesn't attain positive values at all. Okay, so anywhere you look, you only see negative voltages. So you would obviously determine that the transmitted sequence was a string of zeros. Okay, whereas there was a 1 in it, and you couldn't detect the 1. So that's a gross error. Now this case, it does reach positive values, but you can see that the positive voltage that is reached is small. So in this case, of course, with a perfect detector, you can always detect this 1, but the detectors also have some error. So if the error happens to be greater than this value, you may not detect it correctly. Okay, so this definitely gives you errors. This may give you errors depending on how robust, how accurate the detector is, and this is a very good case. So this is the fundamental problem with transmitting data across a pair of wires. The wire is not perfect, and you think you are sending digital data. The first thing that happens is, even if you send quantized levels that change abruptly like this, right? That is the meaning of a digital data. It has discrete levels, and it also changes at discrete some instance of time. I mean, usually some periodic instance of time. But the output will not be like that. The output shows a continuous voltage, that is a continuous amplitude, meaning the output amplitude is not discrete. It doesn't consist of 2 values or any number of finite values. Okay, so that is one problem. That itself is not a big issue because you can always map a range of output amplitudes to one symbol. Okay, it's not like you are saying if I receive exactly 1 volt, I'll say it's a 1. No, that's not the case, right? You are saying if it is more than 0, it's a 1. So that problem, the first problem is got rid of by appropriate thresholding, right? So you map a range of output amplitudes to one symbol. So if you have a number of symbols and you have infinite number of output amplitudes, infinite number of levels, but you map a range to a particular symbol and you choose the ranges appropriately. Now the problem is, even with appropriately chosen ranges, if your wire is bad enough, meaning if your R and C are large enough, you can have a case where it's very difficult to distinguish which range it is in, or where it's impossible, simply because the signal at the output doesn't reach the amplitude it's supposed to reach. Okay, so this is the basic problem in digital communications. So how do we get rid of it is the topic of the course. Okay, so now here we saw that how bad the problem is depends on how much the RC time constant is, or alternatively how much the cutoff frequency of the filter is. Okay, so basically we will see that it is related to high frequency attenuation. Okay, so if you have a very large time constant or a small cutoff frequency, then you will have bigger problems transmitting digital data, right? So this will be a problem for everything. To transmit data over any pair of wires, this can be an issue. Now it could be that in most of the cases, in many cases that you see, the RC time constant is small enough. When I say small, it's compared to what? These are dimension quantities, so I have to compare it to something. What is, when I say small? So in this particular case, if this is the symbol rate, if tau is much smaller than Ts, I don't have any problem. And this is the kind of case that you encounter normally, let's say in the lab, when you connect, each time you connect a pair of wires to take some signals from the, let's say the signal generator to the output, you don't think of all this. You don't have to think of all of these impairments, right? So that is simply because the time constant in that case is much smaller than the time period that you are interested in. Okay, but you will see cases where the time constant is comparable to or much larger than the time period that you are interested in. Okay, and that is true for the cases that we saw earlier. So if you look at any of these cases, let's say transmitting DSL data over a phone line, right? The phone line has a very low bandwidth, and you try to transmit DSL data, and even the traditional ADSL has a bandwidth of, I think, 384 kilobits per second. compare this to voice, which has a 4 kilohertz bandwidth. Okay, so it's almost like 50 times larger bandwidth or something. So voice goes through the cable without any problem. Voice is not digital signal, but I'm just concentrating on the frequency content of the signal. But DSL, when it goes through if you transmit this 1-0 kind of binary digital data through a telephone line, on the other side you will absolutely not be able to recognize the 1-0 data. So this whole DSL modem is about transmitting it in a correct way so that you can recover it properly. Right? Similarly for Ethernet, if you look at the output of even a 100 megabits per second Ethernet line, you connect it to an oscilloscope and see, you will not see anything like this. Okay? Firstly, it's not a two-level digital data. One thing I have to say here is that digital data does not have to have just two levels. We don't need only binary digital data. You can have 5 levels or 7 levels or whatever. You use whatever is convenient. And it turns out that in Ethernet, in gigabit Ethernet, you use 5 levels. Okay? But if you look at the output at the cable, you will not see 5 different levels. You will see a whole mess of things. Okay? And similarly for USB or any other case. Now, I think you all use PCBs in the lab. Again, when you are using PCBs to, let's say, transmit data from one digital chip to another, you don't think of all this. Again, that's because the time constant in that case happens to be much smaller than the period of the signal. Now, there are cases where the time constant is much more than the period of the signal. So, what is happening is the amount of data you transmit has been increasing constantly. As you know, the hard disk capacity is increasing, the data rates has been increasing, the amount of stuff that you want to download is increasing, everything is increasing, right? So, the way to accommodate that is to either have more wires to accommodate all this data, or you use the same number of wires but send more data in the same amount of time. That is, you send the data faster and faster. Now, you can use more wires. That is a possible solution, but that's an expensive solution because you have to actually change the infrastructure, right? So, let's say I didn't have this gigabit Ethernet card, right? Many of you have a gigabit Ethernet card in your computer, but I had only 100 megabits per second cards, and I had to transmit 1000 megabits per second. Then I had to have 10 cards and 10 cables. I mean, you can already see that that's an impossible thing to do. So, what we attempt to do is to transmit 1 gigabits per second over the same wire, right? So, naturally, with progress in communications and the amount of data storage and everything, the time periods of the signals that you want are decreasing. So, even though wires are not getting worse, it's not like the wires are getting worse. It's not like the time constant of the wire is getting any worse, but it's just that the period of the data that you want to send is getting smaller and smaller. Okay? The wires are in fact getting better, but not at the same rate that the periods have been decreasing. Okay? So, it's not like you use 10 times better wire for this than this one. Okay? You use almost the same wire. It may be slightly improved, but you want to send 10 times faster data. So, you have 10 times smaller amount of time to send a bit and detect a bit and so on. Okay? So, that is the problem. So, the amount of data you want to send is increasing. So, because of that, the data rates have been increasing. The data rates have been increasing because you can't multiply the infrastructure so many times. If you want to send 10 times the data, you can't put 10 times as many wires or 10 times as many traces on a PCB. You can try to do that, but then it becomes big and becomes expensive and so on. So, that's why you try to use the same infrastructure and send data faster and faster. Okay? The same thing on a package. Again, the same. So, you are sending all this data and that comes out of some chip, right? So, the data that the chip is processing is also getting faster. So, if you put it in the same package, what was a good package 5 years ago for that data rate is not good enough now, right? And the package also has been improving, but again, not at the same rate as the demand for data rate. Similarly, that goes for links on a chip and so on. Okay? And one set of wires that has been getting worse is the wires on a chip, right? The geometry, the size of transistors on chip have been decreasing, but it's useless if you just shrink the geometry of the transistors, but if you had the same size of wires. To shrink the size of the chip and pack more functionality into the chip, you also have to shrink the size of wires. So, it turns out that the wires have been becoming poorer and poorer because you have thinner and thinner wires, and that means more and more resistance and so on. So, on a chip, the problem is particularly compounded because you want higher and higher speeds, but the wires have been getting worse and worse. Okay? So, the data rates are increasing. You can't multiply the infrastructure. So the infrastructure is used loosely here. It's not some big installation. It is in case of Ethernet and so on. But I'm even talking about having a larger PCB and things like that. Okay. This is because it's too expensive. So you multiply the speed instead. So this naturally gives you this problem. So if tau is much less than Ts, you have no problems. But Ts is constantly reducing. So you will always run into this scenario. Okay. And you can open up real systems or look it up on Wikipedia or something and see. So if you look at 10 megabits per second Ethernet, you don't have very sophisticated transmitters and receivers because you don't need it. Whereas 100 it's more sophisticated and 1000 is very sophisticated, and 10,000 it's on the borderline of doable. It's really difficult to do. Okay. So the higher speeds give you data impairments and you have to correct them. Okay. So this is basically the topic of the course. How do you send high speed data over a pair of wires, and particularly over a pair of wires that may not have sufficient bandwidth to carry the signal. That is, the period of the signal is much smaller than the time constant associated with the pair of wire. Okay. Not all wires can be described with a single number like R times C. It also has inductances and so on, but you get the idea. Okay. So that's the topic of this course, and it's called broadband. Because why is it called broadband? How do you get a narrowband signal? How do you get the signals to be narrowband in a radio? No, that is after you. How do you generate the signal? Why does it become a narrowband signal? See, this narrowband and broadband are not some absolute limits, right? A wireless LAN signal can have 54 megabits per second bandwidth. That is still a narrowband signal. Whereas, let's say your telephone signal or maybe some low speed, the older versions of USB have a few kilobit, maybe a few megabits per second. That is still broadband. Why is that? Exactly. So you modulate the stream onto a high frequency carrier. Okay. Again, high and low are not absolute values here. They are in relation to the bandwidth of the signal. So what do you do in wireless? You start with a baseband signal. Very simply, you multiply it by sinusoid at Fc. So what comes out is centered around Fc and has a bandwidth of 2 FB. Okay, this is a very basic up conversion that you do. Okay. Now you have this carrier, right? So you have a carrier with which you multiply and turn this into a narrowband signal at a center frequency Fc. It's not that the bandwidth of the signal has become smaller, right? It's just that in relation to the center frequency of this, here it was wide and here it is narrow. Okay, that's all. So what we mean by broadband signals here is that when transmitting data over wires, we don't use modulation like this. The reason we use modulation in a radio is because it is being transmitted over a common medium. Okay. So if I want to transmit over air and you want to transmit over air at the same time, either we have to stand far apart from each other, or maybe we like each other too much and we want to stay here. Then you use FC1, I use FC2, and they go to different frequencies. Okay. So that's how somebody will be able to distinguish the signals from me and the signals from you. Whereas on a wire we don't need to do that. It's a confined medium. So it will almost always be a broadband signal like this. So that's about broadband signals, and the title says VLSI broadband communication circuits. What we mean is we are looking at IC design for transmitting and receiving broadband signals. So basically we will concentrate on how to make circuits on a chip that will transmit these things effectively and receive them properly. So we discussed one major source of impairment. The wire itself has parasitic elements, and that modifies the signal in a way that you can't distinguish between different digital symbols. There are other things as well. So we said that this is a confined medium. So when you send a signal in a wire, no other signal interferes with it. Now that is not entirely true, right? So you have, let's say, one pair of wires here and another pair of wires here. You transmit V1 on this, you transmit V2 on this one. Now ideally, V3 should be related only to V1 and V4 should be related only to V2. But if these two pairs of wires are close to each other, there will be some interaction between the two. For instance, there will be a parasitic capacitance between this wire and these two wires and so on. Okay. So there will be what is known as crosstalk. That is, because you do have multiple pairs of wires in proximity, you do have communication between one channel and a totally different channel. So this is known as crosstalk. So this is another problem that you may have to combat or at least minimize so that you can use the link without being too affected by this. So for instance, if you look at an Ethernet cable, what do you see? How many such pairs are there? 5, 4. There are 4 pairs. Okay. There are 8 wires, right, on the RJ45 connector. So there are 4 pairs and there is no isolation between them. They are all twisted together. So there is a huge amount of crosstalk in Ethernet. So that is another reason why if you look at the output of, if you just like connect one side to the computer, put the other, one of the other pairs to an oscilloscope, you will see total garbage. Okay. So firstly, it's because the wire itself is so long and whatever you transmit on that particular pair itself is not being received properly. And secondly, what is being transmitted on the other 3 pairs also gets coupled to this particular pair. So this is one of the problems. So basically the problems associated with the wires are, as a high frequency attenuation, basically this is related to large time constants. Now this is not the only kind of impairment on a wire. So we only took a very simple case where the wire had a resistance and a parasitic capacitance. Now it will also have inductance and it will also have all kinds of connectors and other impedance discontinuities. Okay, it's not a uniform transmission line, right? So it turns out they also cause many problems. Whenever you have an impedance discontinuity, you have a reflection. Okay, this is, you know this from the basic transmission lines course. So for instance, if you have a uniform transmission line that is terminated by an open circuit, right? This has an impedance Z0. On the other side, it has infinity. So if you send a pulse, what do you see? It will keep going back and forth, right? So in a lossless transmission line, it will go back and forth forever. In a lossy transmission line, it will die out. But at least what you see won't be just a step. You will see some more things. Okay, you will see some things like this. And these reflections do occur because simply you can't make a uniform medium. For instance, I mean, the Ethernet cable, it's no use having just a cable. Firstly, it's not uniform at all. Even if the cable were uniform, you have to connect it somewhere. The moment you make a connector, that becomes a impedance discontinuity. Okay. So there are various such things which impair the signal. So for instance, let's take an extreme case where a transmission line is terminated by an open circuit and you drive it with a ideal voltage source at one end. Let's again take our favorite test signal. It's -1 volt and it becomes +1 for one symbol period and then goes back to -1. What do you see at this end if you send a pulse like this? Or let's take an even simpler case. Let's say it's just a step. Okay. Let's say it's a step like this. What do you see here? Let's say it is an ideal lossless transmission line. Ringing. What is the frequency of the ringing? TS. Firstly, there is no TS in this at all, right? It's just a step. Let's say the delay of this line is TD. What you see is the output will rise up if you apply a step after a delay, and then it will go to twice the steady state value. Okay, because it's an open circuit. It comes, the wave comes back here, gets reflected and goes back. So 2 TD later, you will see another reflection. So you will see ringing like this. The period of the ringing will be 4 times TD. So every 2 TD it will alternate. Okay, and if it's a lossy transmission line, it won't go all the way up and it won't last indefinitely. It will do something of this sort. Basically, for a signal, at every reflection in this at this end, it will change. I mean, it will experience a step. For the next step to occur, the signal has to go to the other end and get reflected back. So that delay is twice the delay of the transmission line. So clearly here also you can see that you can run into problems if the ringing is so much that it takes you to it reverses the polarity of the signal. Okay. Okay, and the second one we already discussed. It is crosstalk. What else can be a problem? How do you transmit digital data? You know, that is actually a big problem. That is, we are happily saying that we'll transmit ones and zeros, and the symbol period is TS. Now TS is known. Even if it is known, it's not exactly known. There is always some parts per million type of error. But that can give you significant errors, okay? Because you don't know exactly where the bit starts, where the bit ends, or how long the bit is in many cases, okay? So, the third issue with transmitting digital data is timing. That is, knowing the bit interval and also knowing where in the bit to sample, right? Not every place may be ideal. You may want to sample just before the transition, or at least you want to sample where the probability of error is the smallest. Okay, how do you find that? That is also a problem. Okay, we can discuss this a little more in the next class, but that is a big problem. What is the simplest way of solving this? How can I make sure that I always know the frequency of the transmitted? How do you generate a digital signal? How do you generate the timing of a digital signal? From a clock, right? There is a clock that typically clocks a flip-flop or something, and you get the digital data out. So the easiest thing you can do is provide the clock in addition to data. Okay? So whenever you have a communication link, you don't just have one link for the data, you have one link for the data, another one for the clock. That is always possible. What's the problem with this? Clock skew. Okay, that's a problem, but what's an even lower, that is one of the problems. Meaning, the delay for the clock may not be exactly same as the delay for the data. So even though when you sent it, the clock is at the exact position required, when you receive it, it may not be at the exact position required to receive the signal. Now you have solved the problem of knowing what the bit interval is, right? Because the clock frequency will not change. The bit period will not change. So on the other side, when you receive the clock, you know exactly the interval of the clock and you know exactly the bit interval. But you may not know, the clock may have got delayed by a different amount compared to data. So that can be a problem. What is another problem with this? No, that is all like more detail. I am talking about more of economics type of thing. I mean, it's the same thing as initially, before I said that I can't use two wires if I want to double the data rate because it's too expensive. That is always an option. So here it's the same thing, right? To transmit the same data reliably, I have to send both the data and the clock. So that may be too expensive, so maybe I choose not to do that. So if I have some way of recovering the clock from the data, I would prefer that compared to sending the data separately. Okay. So all this is a question of whether it makes sense economically in a particular system or not. So in some cases you do use parallelizing, right? Instead of sending one signal at 1 gigabits per second, maybe it makes sense to have 4 wires each operating at 250 megabits per second. So in the same way, maybe making the clock recovery circuit is too expensive or it's too much effort. In that case, you send the clock separately. So you have both cases. You have cases where the clock is sent separately and you have cases where it is not sent. If it's not sent, you have to generate both the timing, both the frequency of the data and the phase of the clock. If it is sent, you may have to correct for the phase. So similarly for multiplexing or demultiplexing, whether you want to have one wire operating at a high frequency or many wires operating at low frequency, it's also a matter of cost and how complex it is and so on. So if you choose the highest data rate and choose only one wire, it uses the smallest amount of infrastructure, but it's also most complicated to do signal processing and recover what was being sent. Now if you if you have a whole bunch of wires at a very low data rate, it's very easy to recover the data, but then it becomes too expensive because you have to have a transmitter and receiver for each one of them, and that may be too expensive. So there are both cases, okay? So in practice also.